All right, let's talk a little bit about the mean value theorem for integrals. So we've seen that the area of the region under the curve is greater than the area of an inscribed rectangle and less than the area of the circumscribed rectangle. In other words, the area of the region under the curve is going to be smaller than the biggest rectangle that can fit outside the curve, and it's going to be larger than the smallest rectangle that can fit underneath the curve. It touches the minimum. Okay, the actual area is trapped in somewhere inside there. Okay, the mean value theorem for integrals states that somewhere between those two rectangles is a rectangle whose area is precisely equal to the area of the region under the curve. Okay, so at some point here, if you go straight up from there and get the height of that function at that point, you can draw a rectangle that will have the exact same area as the area under the curve. All right, so if f is continuous on a closed interval a to b, then there exists a number in C in the closed interval a to b such that the definite integral of the function is equal to f of c times b minus a. This is kind of like height, and this is the width. Okay, so the definite integral is equal to the area of, this is pretty essentially the area of a rectangle that's given by the height at some point of the function on that interval. Okay, so let's talk a little bit about average value of a function. So the average value of f of c given in the mean value theorem for integrals is called, or the value of f of c rather, given in the mean value theorem for integrals is called the average value of f on the interval. Remember, the mean value theorem said that the integral from a to b of f of x dx is equal to f of c times b minus a. So it's like, this is two different ways to look at area. This is the area under the curve, and f of c is that point, or that sweet spot right here, that when you multiply it by the width gives you an area of a rectangle that is equivalent to the area under the curve. Well, if you think of f of c as the height and b minus a as the width, if I divide both sides by b minus a, I would get 1 over b minus a times the integral of f of x dx equals f of c. So if you think again that the definite integral represents area and I divide by the width, I'm going to get the height, or the value, the average height or the average value of the function. Okay, so the definition of average value of a function on an interval is 1 divided by the width of the interval times the integral of the function over the interval. Okay, that will give you the average value of a function. To see why the average value of f is defined in this way, suppose that you partition a to b into n subintervals of equal width, delta x equals b minus a over n. If c is any point in the ith subinterval, the arithmetic average or mean of the function values at the ci's is given by, well, to get average, don't you add everything up and divide by how many? So you would add up all the function values at those different subintervals and divide by the number of subintervals. Well, by multiplying and dividing by b minus a, you can write the average as 1 over b minus a times the Riemann sum. Now, if you take the limit of the Riemann sum, that pops this Riemann sum into a definite integral. So this development of the average value of a function on an interval is only one of the many practical uses of definite integrals to represent the summation process. So let's do one. Let's find the average value of f of x equals 3x squared minus 2x on the interval 1 to 4. So the average value is 1 over b minus a times the definite integral. So in this case, it's 1 over 4 minus 1, or 1/3, times the definite integral from 1 to 3 of our function. Well, the antiderivative of 3x squared minus 2x is x cubed minus x squared, the 1/3 from the 1 over b minus a. So we're going to plug in 4 and 1, subtract, and then multiply that answer by 1/3. So plugged in 4, plugged in 1, subtracting here, multiply by 1/3, you get 48/3. So the function from 1 to 4 starts at 1 and curves up to a height of 40. Okay? Well, since it's curved, you can't just divide, you can't just add 40 and 1 and divide by 2, since it's curved. Okay? What you have to do is find the area under the curve and divide by the width. That's what we did. The area under the curve would be 48. We divided by the width, which is 3, and you get 16. That means that if you drew a line at a height of 16 and sectioned off a rectangle at height of 16 over this interval, that rectangle would have the same area as the area under the curve. Okay? So let's look at the speed of sound. At different altitudes in the Earth's atmosphere, sound travels at different speeds. The speed of sound, S of x, in meters per second, can be modeled by this function, where x is the altitude in kilometers. What is the average speed of sound over the interval 0 to 80? Okay, so essentially what we're doing is taking all these piecewise functions together. Break the interval into 5 parts and integrate over each part, because each part has a separate function. So I integrate from 0 to 11.5, 11.5 to 22, and so forth and so on. So the first one gives me 3,657. Next one gives me, and the next one, and the next one. In each case, I'm anti-differentiating and plugging in the upper and lower limits and subtracting. So I get all those. Now, you add all of those answers together to get what is essentially the area under this graph. Okay? Now, to get the average, all you do is divide by the time interval, or the interval. So the average speed of sound from 0 to kilometers to an altitude of 80 kilometers is 1 over 80 times the definite integral. Well, we found the definite integral, so it's 1 over 80 times 24,640, which is approximately 308 meters per second. All right, cool.